Hi everyone, welcome to this new video series on long short-term memory. And we will also cover gated recurrent units, GRUs, after LSTM. So these models are improvisation to standard recurrent neural network. We will look into the details of sequential data processing and some of the challenges that we face while doing or while using traditional recurrent neural networks. LSTM and GRUs are two very powerful and sophisticated architectures, and they have emerged as powerful solutions to address some of the issues like vanishing gradient problem. And these architectures essentially enable the models to capture some of the intricate details or patterns within the sequence uh, data or text, for example. LSTM and GRUs are also slightly complicated, so we will give special focus on the technical details of the architecture, and we will compare each of these models or the variation and talk about the strengths and weaknesses. So the coverage in this video series on LSTM and GRUs will be the inner workings of the components of the architecture. And we will take the examples, typical examples like, text processing or, text classification using sentiment analysis as a focus and also time series analysis. So, who's this video for? Anyone, beginner or experienced machine learning practitioner. Um, and we will be basically focusing on the technical understanding of the architectures like LSTM and GRUs. Prior skills, yes, we need to have understanding of machine learning frameworks and a deep learning framework, and also a fair understanding of data and matrices, and also linear transformation. So the topics that we will cover in this discussion, we will talk about the background and some of the issues that we discussed at the end of the RNN series, and we'll talk about those, like, from the recap perspective. We'll talk about the key components of LSTM, and the components are forget gate, input gate, and output gate. And then we will summarize. So let's talk about the background or some of the issues that we discussed early on. One of the problems that standard neural nets face is the vanishing gradient problem. So what happens during the back propagation? The gradients can sometimes really diminish very fast and also diminish exponentially. So this happens during the back propagation, especially when we have the network, which are very, very deep. And it's very common to have a deep neural nets in case of sequence data processing. So the impact of this is the model weights. When we compute the model weights, they are very little or sometimes negligibly very, very small. And this leads to a very slow and kind of stalled training process. And this affects the long-term dependencies, which is basically a key requirement in majority of the NLP application. So LSTM and GRUs are, sort of mitigations options because the architecture allows for special provisions of memories and, storing the long and also the short-term memory, and that allows for better handling of the long-term dependencies. So another the problem with the gradient is called the exploding gradient, where the just the opposite happens when the gradients become extremely large. So the consequence of this is the model becomes unstable, and the convergence, is an issue in that case. In other words, it can cause the model to oscillate or diverge during the training process. So, in case of exploding gradient, the mitigation strategy can be, something like gradient clipping, where if the gradient exceeds a certain threshold, then we can, clip it or bring it to a lower value. So these are the solutions to address the vanishing and the exploding gradient. Difficulty in capturing the long-term dependencies, and that's precisely what the objective of LSTM and GRUs are. While LSTM and GRUs address uh, quite significantly the issue of long-term dependencies, and they give you a very improved results, but they are not really 100% solution, because the problem of long-term dependency is pretty huge, and it's also a ongoing research and advancement techniques, where the researchers are continuously looking to improve the model. Of late, we have transformer-based and the BERT-based language models. More popularly like large language model, these models handle the long-term dependency in a much improved manner. So just like the long-term dependencies, the parallelization is another key issue while dealing with the sequence data. LSTM and GRUs also, they do not give you a perfect solution to parallelize the training process, but the architecture allows for some amount of parallelization, which we will discuss while dissecting the inner details of the LSTM and GRUs. Lack of global context understanding, this is also a global problem with most of the sequence models. And the true solution, or rather significant solutions, improvement in the model can be achieved by using advanced architectures like transformer and BERT or large language models. Memory and computationally intensive, this also becomes an issue with standard neural, or rather standard recurrent neural nets, and they become less suitable as a deployment option when we talk about the sequence data. So LSTM and GRUs, they have explicit memory, cells and definitions, and that allows the model to capture the information in terms of long-term and also the short-term, definitions. Again, this is not exclusive. The problem is not exclusive to RNN and LSTM and GRUs. As we discussed, this is more like a global issue, and advanced architectures which are based on attention and self-attention, they address this issue of memory and computations in a better way. So the history of LSTM, it was introduced towards the early 2000, or you can say late 90s. Um, and the key idea here in LSTM is to selectively, we should be able to forget and pick information from a sequence of text. And we'll see how that is actually achieved by the architectures. So some of the key components. Um, so LSTM, we have a special provision and a definition for memory cells. And these cells allow us to, store the data over a longer sequences. We also have input gates and forget gates and output gates. We will dissect each of these gates in terms of intuition and also the technical architecture. So what are memories in LSTM? These are designed patterns within the architecture to store information over a long sequence of text. Compared to RNN, where we have just one, memory, which is a hidden state, LSTM, they have two separate memory components. One is called cell state, and the other one is called hidden state. The cell state is used for long-term memory, and a hidden state is used for short-term memory. So as the cell set is designed for long-term, so that means information or the text will be processed over a longer sequences, and the aggregated value or representative value over the sequences will be stored in the cell state. And that's what we mean by saying ability to provide a better contextualization or a long-term dependency. So LSTMs enable the long-term dependencies by using the special provision called cell state. Hidden state is a short-term memory where the input is provided and that input is scaled in terms of linear transformation, and the output that you get is called hidden state. This is pretty much the same that we saw in recurrent neural nets. Essentially, the information captured by the hidden state is the current input and the previous hidden state, which is exactly what we do in the recurrent neural nets. So the architecture of LSTM, let's try to compare with the traditional recurrent neural nets where the input is the at the time step, let's say xt, and the input is in terms of embedding. For example, this is a three-dimensional embedding, and the hidden state can be the size that we want. And in this case, we have a five-dimension hidden state representation. And essentially, this is the time step, and this is where the linear transformation actually happens. And this is a recursive process, so that means unrolling, as we saw in the recurrent neural net description. Now, let's compare the LSTM with the standard recurrent neural nets. So we have two memory here. One is the cell state, the other one is a hidden state. The hidden state is a short term, the cell state is for a long term. These are nothing but vector representation. These can be configured. Typically, the dimensions of the cell state and a hidden state is kept the same. Let's say 32 dimension definition for cell state. The hidden state is also defined in terms of 32 dimension, but it can be also different. In this picture, you see here, this is a 5-dimension hidden state. This is a 3-dimension hidden state. Input is again a vector representation. In most cases, is going to be embeddings. It could be Glove, it could be Fastex, it could be Elmo, it could be any custom embedding like Transformer, BERT, or Hugging Face provided embeddings. So these are your input, and this is your previous hidden state. Now the first gate is called forget gate. In this forget gate, what happens is these two inputs are combined and they are applied in terms of sigmoid activation. And this allows for the selective forgetting or retaining of information. This is what we will see subsequently in detail how it is actually achieved. So the first gate is called forget gate. Next one is called input gate. So in this particular input, again, the concatenation of the previous hidden and the input embeddings, and they are applied. sigmoid transformation. And after that, we have a tan h over whatever we get is the output. And the intuition here is how much of the new information, which is basically this input here, how much of the new information we want to add to the cell state. This is precisely the intuitive meaning of the input gate. Next gate is called the output gate. Now, in this particular gate, again some linear transformation, and with that linear transformation we will achieve the output, which is how much to expose as the hidden state. That means the uh, hidden state after this particular time period. Let's say this is time period t, then what would be the hidden state representation when we have processed the cell workings here. So this will define the hidden state at this time step, and similarly you have a cell state as well. So this is what you see here compared to standard recurrent neural net. The LSTMs are extremely computationally intense. Um, so let's see how the forget gate actually operates. So it takes the input. There are two inputs. One is the hidden state and the current input. Both are nothing but embeddings. And then we apply a sigmoid activation on both of these, and that will determine how much of the previous cell state has to be retained or forgotten. So let's see the computation here. So you have the cell state and also the previous hidden state here, and the input is going to be provided at that particular time step, and both are nothing but embeddings. Now you have to concatenate. The first what we need to do is we concatenate the previous um, hidden state and also the current input embeddings. So that's the concatenation here. So the embedding size is 3, and this is 3 here, and the memory vector size, which is the hidden state representation, and that's the size of 5. So when you join them together, you get a longer vector representation. By looking at this, the first 5 are from the memory, which is the hidden state, and the last 3 are nothing but the input embedding. So that's the joining of these two uh, together before it goes to the forget gate. All right, so why we concatenate? The reason why we do so is to have a better understanding of the previous hidden state and also the current input. So now for each of the gate, we also need to do a linear transformation of the embedded vector representation by using the weights here. So the forget gate will also have a weights representation and the bias input. So now you have three things. Here is the concatenated embedding, and then the weights here and the bias. These three things will be used to do the linear transformation. The weights matrices also needs to be defined. The size of the weights matrix is nothing but the hidden size representation and the concatenation of after concatenation, whatever is the specification here. So this is how the weights matrix will look like, and this is how the bias inputs. So when you concatenate, you write like, the hidden state, comma, the current input, and that goes into the input of the sigmoid activation. So that input, so this is your concatenated embedding, and this is where you have the weights and biases, and these two inputs will be used to do a linear transformation. So this is the linear transformation. So that means we multiply the weights. And this is exactly what we saw in the linear regression also, WTX. plus B. And that's the output that you get here. Okay, so after you apply the sigmoid on the transformation, you get the output, which is FT, forget gate output. And this FT is nothing but the sigmoid, activation. You notice here the values are between 0 and 1. This is precisely what is the magic being done by the forget gate of the LSTM. So that means the values which are closer to 1 will be retained, and the values which are closer to 0 kind of, forgotten. So in a way, the first element we have zero point 0.9, so that means we will store 90% of the first dimension of the cell state. Similarly, the second element is 9.94. That means that would be 94% of the second element of the cell state, and so on and so forth. So that the last one that you see here is the 5%. That means we are going to retain 5% of the fifth dimension of the cell state. So this is how the LSTM, understands the importance of the dimension. So in the cell state, we are controlling the cell state values or the in the dimension each of the dimensions by applying the output of the sigmoid transformation or activation. And now we're going to apply. So there's the blue cross that you see here. That is where we're going to apply. That means we're going to multiply the output of the sigmoid transformation or activation with the cell state. That's precisely what will happen at the as the output of this, a cross sign here. So what does all this mean? It means, let's say the scenario one, the forget gate output is 0.05. It means the model decides to forget a significant chunk of the cell state on that particular dimension. Only 5% of the information is going to be retained. So the new cell state would be, let's say the original value is 2, so it's going to be multiplied by 0.05. So it's going to retain only 0.1. Let's say the another scenario, zero point 0.09, and that means 90% of the cell state information will be retained. Let's say the original value is 2 and multiplied by zero point 0.9, so that gives you 1.8. So the result of the forget gate after we do a element-wise multiplication, essentially what we're doing is scaling. And the basis of scaling is the output of the sigmoid activation, which gives you the results between 0 and 1. Closer to 1 means you're going to retain most of the information. Closer to 0 means you're going to lose or, forget most of the information. So this is how we effectively control the how much of information from the previous cell state we want to retain in the current time step. And this is exactly how each of the cell in the LSTM will function. So the value closer to 1 is like retaining of the information, and the values closer to 0 means it's going to forget most of the information. So result is you have a new updated cell state which incorporates both of the information like the current input and also the previous cell state. Okay, so after the forget gate, let's talk about the input gate. So in the forget gate, the outcome that we achieved was how much of the previous cell state we would like to carry to the next or the current time step. In the input gate here, we will determine how much of new information should be taken into consideration. That means that how much of new information or new input that we can or we should add to the cell state at the current time step. So essentially, input gate is responsible for controlling the amount of information from the current input into the current cell state. So like in the forget gate, we are going to first do the concatenation of the inputs like the previous hidden state and the current input, which is xt, and it will go through the concatenation process. Now we're talking about the second gate, which is basically the input gate. Concatenation, and that gives you the embedding. So here is the input embedding size 3 and the hidden state embedding size 5, and that will result into the embedding of size 8 after the concatenation, and that is represented by ht minus 1 and xt, which is the current input. So the input gate here also requires the weights matrix like the forget gate here. So this is Wi is the input, input gate weights matrix, similarly the bias, and they will be used for linear transformation of the concatenated embeddings. So we're going to apply the weights of the input gate on the concatenated input. For example, here, this is how you do that. The typical linear transformation, similar to what we have been seeing in the linear regression and also recurrent neural nets. So that gives you the output after the activation, and that output is represented using the sigmoid activation here. So essentially, it's nothing but the values would be the size of embedding, which is basically the size of the hidden state. And let's say that is 5, and so the output of the sigmoid activation will also be the size of 5, and the values are going to be between 0 and 1. So closer to 0 means, it's going to be influential, and less influential, and closer to 1 would be more influential. Now, the second step that we have within the input gate is to prepare the future cell state. In order to prepare the future cell state, we need to have a intermediate or candidate cell state defined. And in order to do that, another pair of weights and biases here. So this is weights matrix and the bias matrix, bias vector. And that also goes through the tanh activation. And after that, these two will go through a multiplication, element-wise multiplication here. So that gives you the candidate cell state, which is basically your IT, which is the output of the input gate, and the forget gate and the cell state of the previous time step. All right, so this is the previous time step in the previous gate, which is the forget gate, and that output is now taken into the consideration. All right, so the output of the previous cell state is nothing but to control the cell state in terms of how much information we want to bring from the current input. Essentially, the sigmoid is playing a very big role in each of the gates that we have seen so far. Now, the last one is the output gate, and this output gate is essentially what is going to be the hidden state representation from the current cell. So this is the output. The hidden state is the output of the LSTM, and this is passed to the next time step. So again, this will also go through the first elementary process, which is concatenation. So the third gate that we're talking about here is the output gate. And similarly, you have the hidden state and the input here, and that will be concatenated. Exactly the same process here. And now the apply the linear transformation to the concatenated vector using the weights. So this is the fourth set of weights matrix that we have seen. First was the input gate. Second, we talked first was the forget gate, and in the input gate also we had two sets of weights matrix, and now this is the fourth one being used here in the output. Exactly the same process, the linear transformation, and then after that the sigmoid activation. So that's your sigmoid activation here. Now what we do here is the interesting thing, to bring the cell state that we achieved in the previous gate and apply the tanh. Tanh will bring the data between or activation between -1 and +1. So essentially, this is what is happening. The last, what we do is the output of the output gate, and then we multiply element wise the cell state from the previous gate. And that gives you the hidden state representation from the current cell. And that will be passed over to the next cell. So summarizing what we achieved by using the forget gate, here we decided how much of the previous cell state will be brought to the current state or current cell. And the input gate is how much of the current input can be brought into or fed into the cell state. And then we update the candidate cell state, which is the interim one. And using that, we finally output the hidden state, which will be passed over to the next state. Now, all of these is nothing but your, very smart use of sigmoid and tanh, activations. The basic idea is here the embeddings of the tokens, and if these two tokens are similar, they will result in high values when we talk about the sigmoid activation. So the high values mean the similar tokens are going to be preserved, and the tokens which are not related will result in lower values when you apply sigmoid transformation, and that will be forgotten. This is the essence of LSTM. Okay, so let's now assess how LSTMs address some of the issues that we saw in RNN. With the gating mechanism like forget gate and input gate and output gate, that addresses the vanishing and the exploding gradient because we are using the Tannish and the sigmoid activations in between, and that addresses the exploding gradient issues, and also it also addresses the issue of vanishing gradient. So essentially, very smart use of sigmoid and tanh activations. They address the big problem of vanishing gradient, and in turn, that helps us achieve the long-term dependencies issues as well. Yeah, so with the use of gating mechanism and also use of explicit memory definitions, we are now in a position to enable key functionality of or a key requirement of NLP, which is a long-term dependencies. Parallelization is a big topic. LSTM and GRUs do not address parallelization in 100%, but to some extent, the forget gate operations and input gate operations can be parallelized. Global context also is a bigger topic. LSTM and GRUs are first step towards a solution towards contextual understanding, but they are limited when we talk about a true solution for global contextualization. Now, computational intensity, yes, the LSTM and GRUs, they are quite complex in terms of architecture, and hence the requirement of computing resources is also very high. But this is not all exclusive. This problem is not exclusive to only LSTM. They are related to, or they impact almost any deep learning models. So again, this is the active area of research today, with the combination of hardware improvement and some of the algorithmic enhancements. These are being addressed. So what are the variants of LSTM? Let's talk about a couple of variants that I'm going to be showing you in terms of text classification or sentiment analysis using LSTM. So one of the popular one is called stacked LSTM. So here what we do is, here are the LSTM cells. So going in a forward direction, and then we have the inputs at each of the time step, another LSTM layer stacked on top of it. So the top one or the second layer will get the input from the below one. And finally, we can take one output here at the end to classify. This is the architecture that I'll be demonstrating in the next video when we talk about text classification, essentially a sentiment analysis using IMDb dataset. So the benefits of stacked LSTM is pretty huge. I mean, it allows you to get hierarchical information, um, and it is designed, or rather, it is if we stack optimal number of layers, it typically gives a very good result when we talk about text classification. Another variation of LSTM is popularly called bidirectional LSTM. Here we are going to look at the sequences being processed from left to right, and another layer will process the sequences from right to left. So this could be very useful in deciphering some of the intent here. Let's say Apple is something that competitors simply cannot reproduce. Now, this is, we are talking about the Apple as an organization, but here Apple is something that I like to eat. So if you read from left to right, let's say you are here at this point, something, then we wouldn't know, the model will not know whether it is about the fruit or it's about the organization. So if we have a model which can read from left to right and also right to left, then have an aggregated hidden state, it will help the model predict whether the next word or is going to be for for the fruit or for the organization. So the bidirectional LSTMs are very useful when we talk about machine translation or a language to language translation. Essentially, you have a left to right model here, and then the input being given. Similarly, you have a right to left layer, and the same input will be provided to the other layer as well. But the output, when we look at the output, is going to be the output from both of these layers, and they are being aggregated into the output cell. So this is a consolidated view of a sequence from left to right and right to left, and this allows for better predictions. So next, I'm going to show you a demo using a IMDb dataset showing sentiment analysis, and I'll be showing unidirectional LSTM, and also I'll show you the stacked LSTM. So that's it in this video. We'll see you in the next one.